All right, today we are diving into one of the most powerful tools in all of mathematics, the Laplace transform. Seriously, think of it like a secret weapon, one that helps you solve some of the absolute toughest problems calculus can throw at you.
So, let me ask you a question. What if I told you there was a way to take a really nasty calculus problem? You know, one filled with all sorts of derivatives and messy integrals.
And just like that, turn it into a straightforward algebra problem? One you could solve with just basic rules? I know, it sounds almost too good to be true, doesn't it?
Well, it's not. There is a mathematical machine that does exactly that. And today, we're not just going to learn about it. Nope, we are going to build this incredible machine from the ground up, piece by piece.
Okay, so first things first, let's start with an idea you're already familiar with. Think about differentiation and integration. At their core, they're really just transformations. You put one function in, say x cubed, and they spit a totally new function out.
The official name for this is an operator. It's just a fancy term for any operation that takes a function as an input and gives you a new function as the output. So, for example, the derivative operator turns x cubed into 3x squared. It's as simple as that. Now, here's the thing. The most useful operators, the ones we really care about, follow this special golden rule called linearity. Basically, it just means you can transform a complicated function piece by piece. You can pull constants out and break up sums. Now, you're going to want to remember this rule. It is incredibly important later on.
Okay, so here it is. This is the blueprint for our machine. It's a special kind of operator called an integral transform. And here's how it works. It takes our starting function, let's call it f of t, multiplies it by another special function called k, and then it integrates the whole thing. This process transforms our original function of t into a brand new function of a different variable, s.
That k function has a special name. It's called the kernel. And let me tell you, this is the absolute heart of the machine. It's the secret sauce. If you change the kernel, you can build completely different kinds of transformation machines.
So what's the secret ingredient for our machine, the Laplace transform? Well, it's this incredibly simple, elegant exponential function, e to the power of negative s times t. This little guy is the core component that's going to do all the heavy lifting for us.
We just need one last piece for our machine. It's operating range. See, we're not just integrating over some nice clean interval. We're integrating from 0 all the way to infinity. This is what's called an improper integral, and it's really just defined as the limit of a regular integral as its top boundary heads off towards infinity. And here it is. We've assembled all the parts. This right here is the Laplace transform. We take our input function f of t, multiply it by our kernel, e to the negative st, and integrate from 0 to infinity. Our machine is built. It is now ready for its very first test run. So let's take this machine for a spin with the simplest function I can think of, the constant value 1. First, we just plug it into our definition. Then we do the integration. It's just a standard step you'd see in calculus. And finally, we evaluate the limits to see what we get. And look at that. Our machine takes the simple constant function 1 and transforms it into the clean algebraic function 1 over s. This is the magic right here. A constant in what we call the t world becomes a simple fraction in the s world.
Okay, what about something a little more complex? Let's feed the function f of t equals t into our machine. Now, after a bit of integration by parts, which we'll skip for now, out pops another beautiful result, 1 over s squared. Are you starting to see a pattern here?
Let's try one more. How about the exponential function, e to the at? This one is super important in fields like engineering and physics. Our machine takes it and transforms it into 1 over s minus a. It turns a growing exponential into a simple rational function. Just incredible.
Now, of course, some functions are a little trickier. Finding the transform of sine of 2t, for instance, requires this really clever trick where you do integration by parts twice to create an equation that you can actually solve for the integral. Yeah, it's a bit of work. But the result is just beautiful. And this perfectly illustrates the whole point of our machine. A complex, wavy sine function in the t world becomes this simple, well-behaved algebraic expression in the s world. This is exactly the kind of powerful transformation we were hoping for.
Hey, remember that golden rule we talked about earlier? Linearity? Well, it turns out the Laplace transform is linear, and this is its true superpower. It means if you have a function that's made up of several pieces, like say 5 times t plus 3 times sine of t, You can just transform each little piece separately and then add the results back together.
And that superpower, linearity, is what allows us to build a toolkit. Instead of having to rederive the transform from scratch every single time, we can just use a table of common building block functions. You just look up the transforms for the simple parts and use linearity to assemble the transform for way more complicated functions. This is what makes the Laplace transform so incredibly practical to use.
So there you have it. We've built a machine that literally turns hard calculus, like the kind you find in differential equations, into simple algebra. You transform the problem into the swirl world, solve it with algebra, and then transform back. It's just an incredibly elegant and powerful method. So the only real question left is, what difficult problems could you solve with this machine?